this would be the parent function that's going to create for us a parabola. Right? I almost said parabola because now that's stuck in my head. Okay. So where is the vertex point for this parent function? 0. Okay? 0, 0. When you plug in 0, you get 0. Most of our parent functions, what we're going to call the vertex point, or what truly is the vertex because it turns around in the parabola, is at 0, 0. And then that's why we get to talk about where it gets shifted or reflected or stretched, stuff like this. That's kind of your main point that all transformations are done from, as we'll see. If we shift left and right, we're talking about starting here and shifting left and right from 0 or up and down from 0. If we reflect, we're talking about flipping over that point that's at 0. If we stretch or compress things, usually this one stays the same, and it's all the other things around it that start going towards that vertex or away from it when you stretch and compress it. When you plug in 1 and you square it, you would get 1. And same thing when you plug in -1. And when you plug in 2 and square it, you would get 4. And then if you plugged in 3, you would get 9, etc. What we want to do, because we're going to graph with transformation, so kind of like how we did the step function. Remember how we kind of memorized what the parent function looked like? And then based on that, we just kind of pulled numbers out of the equation, and we said, oh, this is going to make it start, instead of at 0, 0, at 2, 5. And then this is going to make the step be 2 units long instead of 1 unit long, and 3 units apart instead of 1 unit apart. We want to do that with this, too, which means we need to have this memorized. So I basically need to know every time I start graphing something, this is how the parent function looked. It had a vertex at 0, 0. When you went 1 away horizontally, you went 1 up. When you went 2 away horizontally, the points were 4 up. If I can store that information, then I can take an equation that someone gives me, and as long as I know what each number does, I can just stretch, flip, and shift that graph to its new location without having to plug in any points. Okay? But we got to know how it starts and how it looked. So then let's go ahead and record some of the information. So you guys already said, so our vertex was at 0, 0. What is the domain of this function? So we're looking just at the parent function. What is the domain for this? So you're thinking x values left and right. Good. Okay. The domain is all real numbers. Right? You can pick any x value, plug it in, and you're going to have a point on that parabola. It might be really high up there, but you'll get something. Okay? And you can see that by the function, too. There's no number that if you put in here, you couldn't finish this calculation. You can always put something in and square it and get some sort of answer. All right, what about the range? So now we're thinking y values, kind of looking vertically up and down. What would you say are the limits of this function? Kendall? Good. Okay. So y is greater than or equal to 0. So y value-wise, we hit 0. We don't hit anything below that, only things above that. So that's what our range is telling us. All right, for the parent function, what are our x-intercepts or x-intercepts? 0, 0. Is it possible for the parabola to not have any x-intercepts? Yeah, like if this one just got shifted up, it wouldn't cross the x-axis at all, right? Is it possible for it to have more than one x-intercept?
Yeah.
Yes. What's the maximum number it could have? 2, right? It doesn't turn around again, so it can only have 2. And then how do we find x-intercepts? For any equation, how do you find the x-intercepts? Good. Set y equal to 0, and then you solve for x. Okay? And then the solving part kind of depends. With lines, it's not too hard. It was a little harder with absolute value because we had to remember how to solve absolute value stuff. Now when we set y equal to 0, for this one it wouldn't be that hard, right? But if there was a lot of other stuff over here, that's when we would want to use our factoring or our quadratic formula to try and help us find those points. Okay? All right, what's our y-intercept for this? The y-intercept. So where does it cross the y-axis? 0, 0 again. Okay. Will every parabola have a y-intercept? So I can make this one look like it doesn't have a y-intercept right now. Let's say I move it really far to the right. But will it still eventually cross the y-axis? Yeah. These sides are going outward. They just start getting really steep that it's hard for us to see how far they go out. But if you're allowed to travel infinitely in any direction, you would eventually see it cross the y-axis. So they always have one y-intercept, and they could have no, one, or two x-intercepts. Okay? How do we find the Y-intercept when we start doing that with our equation? Good, plug 0 in for x, right? And then that's why you only get 1. Notice if you plug 0 in for y, you have to like square root stuff, so you could possibly get 2 if there was more stuff on this side. But when you plug 0 in for x, all the x's get filled up with 0. It's just one calculation that you're doing to find y. Okay? All right, if you have any notes that you want to add in the verbal description of the graph, anything that's going to help you remember, like that you need to memorize the shape of the graph or anything like that, then make that note. If you don't, then you don't. This is a shape that you're more familiar with. So it's not like the step function where it's something you've never seen before and you don't know what to do. And it should be okay. All right, so then what we're going to do is, like I said, we want to be able to graph, like we did with the step function, with transformations. And we're going to start using the language more correctly. So I know you did some of it in Algebra 2. It's going to be a little bit more intense in Algebra 1, not for the quadratic part. It's basically going to be everything you did in Algebra 2. But depending on how well you understood it or where you were with it, the learning curve is going to be different for everybody, right? So just be aware of that. So what we're going to do is, if I gave you this, oh, actually, let's look at this. Okay, so on the back of this paper is this. I don't know. It's fine in Word, then it gets converted here, and it's only the ones that if, like, Sock made it on his Mac, then when I save it in Word, it's fine, but when I convert it to PDF, it's, like, not fine. But if you see these little boxes or these spaces, they should be minus signs, okay? So if this is on there, these are minus signs. If I gave this to you, you don't have this, okay? This is going to be homework number 1. This is going to be what we're going to start with tomorrow. We're going to graph these functions using transformations. Notice that they're all parabolas, okay? So we're going to talk about shifting left and right, reflections, stretches and compressions, and how to graph using those things instead of just plugging in points. But so if you have the note guide you printed yourself, this was on the next page, so all those problems are in there. If not, then I didn't do this because I was more concerned about class, because you can get these problems at home when you're doing the homework. Then your back page has this chart, okay? So if you printed your own note guide, this is on the next page, the third page. All right, so very much like we did with absolute value, this should seem familiar. We already did something like this, right? But we did it with absolute value graphs and not with quadratic graphs. So what you're going to do is you're going to graph these 7 different equations. And then for each of these equations, you're going to say what the A, the H, and the K value are. Keep in mind that this is on your paper up at the top. This is vertex form of the quadratic. So A is this number that's out here multiplying the perfect square. H is whatever number would be subtracted from x. And K is the number that's being added after the square is completed. So for each equation, you're going to fill in your A, H, and K value. You're going to type it into the calculator and sketch it. You're going to say what the vertex appears to be and whether it opens up or down. Does that make sense to everybody? Yes? No? Okay. So A's, H's, and K's. Let's say we look at number 5 right here. So number 5 says y equals x squared minus 4. You can see it on your paper. So think about this. If this is just x, it's like the parentheses are right there. So we talked about this with absolute value. If there's not a number written here in front multiplying the x squared, what number do we consider that if it's not written, but this is multiplication? 1. Okay, so here the A value is 1. The H value is the number that's being subtracted from x within the perfect square. What number is being subtracted from x in here? 4 is being subtracted after the square is done, but inside of the squaring. So H has to be a number inside of this perfect square. So is there a number being subtracted from x inside of here? No. So what number would it be if we didn't write it, but it's addition and subtraction? 0. Okay. 1 is the number when it's multiplication, because 1 times stuff doesn't change it, which is why it's okay not to write it. But when it's addition and subtraction, it's 0, because adding and subtracting 0 doesn't change. So the H is 0. The K value is what's being added after the perfect square is done. So here our perfect square is done. This is after that. So what's the K value in this problem? -4. So there's my A, H, and K. I type this into the calculator. I can get a sketch. Okay. I would say that the vertex is at wherever it appears to be when I see the sketch in the calculator, and it opens whatever I see when I see the sketch in the calculator. Is that more clear for everybody? Okay. All right, so use your group members. If you need to borrow a calculator, stick your ID or your phone or something back there, and you can borrow a calculator. And go ahead and complete this chart, and then we'll answer some questions about it. Okay, the first thing we want to know is how can we predict whether the graph of the equation will open upward or downward? So look at your list. Okay? Look at all your graphs. How many of them opened downward? One. What was different about that equation than any of the other equations? The negative where? For which value? A. Okay? So here, how can you predict whether the graph will open upward or downward? It's all about A. If A is bigger than 0, which means A is positive, right? That means it's going to open up. If A is less than 0, which means A is negative, then we would expect it to open down. Now, A also does other things. Okay? So you had the parent function on there. Then number 2 said 3x squared, and number 3 said negative 1/2 x squared. So I'm gonna bring this slide back up if you're still copying, but just going back here to look at the first 3 equations. So the first one was the parent function. The second and the third one both changed the A value. Now we already said when the A became negative, that's when we saw it go downward instead of upward. Okay, now ignore the up-down factor for a minute and think about numerically what happened. What was different between your parent function and number 2? When we put a 3 in front of the x squared? How did the graphs look different? Skinnier, okay? So the 3 made the graph skinnier or steeper along the sides. Now, I know that in number 3 it flipped over because of the negative, but what did you notice about the shape of the parabola? What did the 1/2 do to the shape? So the negative flipped it over. I get that, okay? But let's say you flipped it back over and it went up. It still would not be the same as the parent function. What would the 1/2 cause to happen compared to the parent function? So the 3 made it get skinnier or more narrow. The sides were steeper. What is the 1/2 doing to the graph? Wider, yeah, bigger, okay? So basically, when we look at the A value, there's 2 things that we're looking at. The positive negative part of it is telling us whether it opens up or down. And what we're going to talk about tomorrow is we're going to call that a vertical reflection if there's a negative A value, okay? Because it's going to flip it over the x-axis, essentially. Then we look at the number part of it because that tells us whether our graph got steeper or if it got wider. And tomorrow we're basically going to call that a vertical stretch or a vertical compression. Your 3 was like a vertical stretch because it was like someone took the parent function and stretched it out vertically, and that's what would make it look skinnier and steeper. Your 1/2 is like a vertical compression because it's like someone took it and squished it closer together like this, which would make the parabola look like it was going out wider. Okay? So we want to mark also here how it changes in A. So we already talked about whether it opens up or down. But basically, when we look at A and we ignore whether it's positive or negative, so if we just look at the number part of A, that's all these absolute value bars mean. When you're looking at the number of A and you don't care whether it's positive or negative, if that number is smaller than 1, like 1/2, okay, the parabola appears to be wider. Okay? And we said tomorrow we're going to talk about calling this a vertical compression. So that was like number 3. You saw your parabola get wider compared to the parent function. However, if the A value is greater than 1, like number 2, where it said 3x squared, okay, you guys saw the sides get steeper. Okay, I'll say it was more narrow, the parabola. Okay, and we'll talk tomorrow about how we're specifically going to call this a vertical stretch. Okay, so we're trying to get used to this language so that when we list transformations, like on your last test, when you list them for the step function, you just kind of said it moved over here, these were this long, these were this. I didn't make you use the exact language, but now we're going to. So we're going to use things like vertical stretches and compressions. Okay. Up here, if it opens downward, we're actually going to call that a vertical reflection. And then when we shift left and right, those are called translations. Okay. Kind of remember that language from geometry. So summarize how changing the value of h affects the graph of the function. So if we look back, if we try to find the places where the h value changed, that was like number 6 and number 7. Okay? In number 6, you should have had Well, for both 6 and 7, your A value should have been 1. They didn't change. And your K value should have been 0 because nothing was being added or subtracted onto the function after the squaring was done. So the H values are what you're seeing. When this says x plus 3 inside of the perfect square, that means this is determining my H value right here. What value is my H? If it says x plus 3 inside of the parentheses, what is the value of H? Negative 3. Good. Remember, we talked about this with absolute value. The formula already has a minus sign there, so you got to think, what would you put after the minus sign that makes it look like a plus? You would put a negative 3, and that's why it would look like a plus. And then what did you see happen to the graph when you sketched it by putting this negative 3 here? So H is now negative 3. What happened to this graph? Look at your sketch. Okay, it went to the left 3 units, right? Meaning its vertex, instead of being 0, 0 like the original function, is now at negative 3, 0. Okay? And what was our H value for number 7? 2. Okay? And you should have seen that graph move 2 to the right, okay? And meaning its vertex was now at 2, 0. So in our summary, when we talk about H, okay, H is going to be what we call a horizontal translation. That's basically like a horizontal shift, okay? In other words, it's going to shift the graph left or right. But the correct language would be to say there's a horizontal translation 3 units to the left, something like that. Okay? So that's all dependent on H. And then we look at our K values. Okay, so going back to the equations that you graphed, which numbers had K values that changed? Which problem numbers? Yeah, well, 4 and 5. Yeah, good. So 4 and 5. So we talked about number 5, and we said the K value became negative 4. In number 4, your A should have been 1, your H should have been 0, and your K should be 1, because you had plus 1 out there on the end. Okay? What was the vertex for the equation in number 4? When you graphed it, where did you see the vertex at? 0, 1. And what about for number 5? So what is K controlling? Okay, it's controlling the y-coordinate of the vertex, and in this case, that was the y-intercept, okay, which means K is in control of moving your graph vertically, right, up and down. So when we summarize what K does, we're going to say that K is a vertical translation. So very much like H, it just kind of shifts the graph, but the H is a control of the left and right, and the K is in control of up and down. So this is going to shift up or down. So our goal today is to be super familiar with these so that tomorrow when you come in, what we're going to do is we're going to make a little organizer. I know, it's kind of silly, but it will help us keep things organized, okay? It will remind us of all the functions that we've learned, and on the back, it will keep track of all of this different language and how to use it. And then what we're going to try and do is graph some of these functions so that you guys can do those 5 problems that you saw earlier that are going to be homework, number 5, because we already did 4 homeworks, that are going to be homework number 5 where we start graphing the parabola, okay? So your goal for today was to know the parent function of the parabola, recognize what A, H, and K control, and then tomorrow our job is going to be to tighten up the terminology and actually create the graphs by using reflections and translations and compressions and stretches, okay? All right, so we're good.